Lesson 2.3 is polynomial functions of a higher degree. So in other words, we're talking not just your standard parabolas. We're talking powers 3 and 4 today, I believe. Okay. And looking at various pieces about these. So we have a lot of different things we're looking at throughout this lesson. A little bit of vocabulary here. A polynomial is actually made up of a sum or difference of individual monomial terms. Okay. Think about these like x plus 1, multiplied it out. There'd be the x cubed term, an x squared term, an x term, a constant term. Okay, that's what we're talking about with polynomials. These terms are to be written in standard form. Okay, so if you recall, standard form is when you arrange the terms in order by descending degree. So going from highest power to lowest power. And when we talk about that, then the leading coefficient is the coefficient that is in front of the highest power term. And then the constant term is at the end. Okay, so a little bit of vocabulary review there. In this first example, we're going to graph transformation, of monomial functions. So describe, see the word describe there, yes. Describe how to transform the graph of an appropriate monomial function, f of x equals x to the n, into the graph of the given function. They ask us to support our answer graphically and to compute your y-intercept as a check. Okay? Yeah, computer. Nice typo there that you don't realize till you're reading it back.
Computer?
Sure.
Okay. Calculator would be typed.
So, let's start with the describe.
You're right.
Okay? What do you see going on in example A when we start talking about describing the transformations? What do you see, Logan?
Personally, I see that moving of left 1.
Okay.
But that's just my thoughts.
A plus 1 in the parentheses is going to tell my graph to move to, if I use the official word, translate, left 1. What else do you see?
That 4 out front, that's going to make it a vertical stretch.
Okay.
Back to a 4.
Multiplying by 4 out front, so multiplying by a number larger than 1 out front is a vertical stretch. So we're going to have a vertical stretch by a factor of 1. And what is the original graph that this is all being done to?
The cube.
Okay, y equals x cubed, yes? And that is something that in my definition, I'm going to state, because it's not always like in this problem it's x cubed. It won't always be the same graph. So in my notes I have written that we're going to translate the graph of y equals x cubed, 1 unit left, and a vertical stretch by a factor of 4. Okay? I'm going to put that in this little open area here. Translate the graph of y equals x cubed, 4 units to the left.
No.
And?
No. 1 unit left.
Yep. Okay. I agree. And I was just coming up with that issue of...
I think you computered it wrong.
I did computer it wrong. Okay, translate the graph of y equals x cubed, 1 unit to the left, and vertical stretch by a factor of 4. Okay. Sorry, your teacher's on the struggle bus this morning, I guess.
Yeah. The first day back is always rough.
It is.
Like.
Okay, guys. So that was one thing we were asked to do. We were asked to describe how to transform the graph an appropriate monomial function, which our monomial function in this case was x cubed. Now, what does that look like?
Well, the cubed function is that little, like, I don't even, like, that little
That.
baby thing.
Okay, he's drawing it in the air. You guys have that visual, yes? Okay? Now,
That's a lot of Y's.
okay, my Y's, I did 8 up and 8 down.
Why?
Because 2 cubed is.
Okay,
Get it?
so, first of all, let's think about x cubed, the basic graph, y equals x cubed. What points does it go through?
0, typically.
0, 0,
Does it go 1, 1?
1, 1, because if you put in 1, 1 to the third is 1.
Negative 1.
If you put in negative 1, negative 1 to the third is negative 1. What about if you put in 2? What's 2 to the third?
8.
8. That's me going up 8. What's negative 2 to the third?
Negative 8.
Negative 8. So right here, I'm just going to do this as a dotted line. Here's that original graph. That's what y equals x cubed looks like, yes? That's the cubing graph. That's one of your 12 graphs that you're supposed to have a good mental image of. Okay? I just basically found those points. Basically, I just plugged values in, right? And cubed them. Now, our directions, our graph moved left 1. So if we move it left 1, what happens? Instead of going through 0, 0, what's it going to do?
0, negative 1.
How about negative 1, 0?
Same thing.
Basically the same thing.
Not exactly the same thing, but I understand what you're saying.
Let it.
Okay, so basically, and I'm not going to write them all in, but to translate left 1, we take each of those 5 points we made and we move it left 1, yes? Okay. What about a vertical stretch by a factor of 4?
You would take the y values and multiply them by 4.
Okay, a vertical stretch, you're multiplying the vertical values, so we're multiplying the y values by a factor of 4. Well, 0, 0 is now negative 1, 0, but when you multiply 0 by 4, you're still going to be at 0, yes? Okay, what about this 1, 1? When I multiply that y value by 1,
1, 4.
it becomes 1, 4. When I move it left 1, it's actually going to be, instead of being at 0, 1, it's going to be up at,
Just go over 1 up 4.
yeah, we're going to be there at 0, 4.
Then you can go over 2 up 32.
And I'm skipping that part, but okay. My point of 2, 8, well, yes, we'd have to move it left 1, so it becomes 1, 8. But when you vertical stretch that by 4, it's 1, 32. Pretend it's up there, okay? Over here, the negative 1, well, it's going to move left, and it's going to be at negative 2, negative 1. But when you multiply negative 1 by 4, we're going to be at a negative 4. Okay? Now, what's this look like? A skinnier version of our original graph. Okay?
No.
I'm not the best at drawing these, but you get the idea. It's a skinnier version. The twist in the middle is less visible. Okay? So that is us supporting our answer graphically. Okay, and again, I'm trying to help you put all the pieces of these graphs together. So we're not just relying on the calculator. We had one more thing to do here. We were told to compute your y-intercept as a check. How do you do y-intercepts?
You type it in the computer.
No.
Compute it.
How do we compute y-intercepts?
And just be 4.
Yeah, you could just do it trace.
Y-intercepts.
It's 0. It's x equals 0.
Y-intercepts happen when x is 0, yes?
Yeah.
So if you take in 0 and plug it into that original equation, so basically finding g of 0, 4 times 0 plus 1 raised to the third. We know what's supposed to come out according to my graph over here, but this is our check, okay? In parentheses, 0 plus 1 is 1. 1 to the third is 1. 4 times 1? 4. Is that what we expected it to come out as?
I mean, kind of, yeah.
That's what we have right here in green, isn't it?
Yeah.
Okay, so that was your check of your y-intercept. Putting 0 in for x, because that's always easy. 0 is always the easiest number to plug in. Put in 0, we see that it works. Okay, questions on that one? Okay, let's look at B. Same type things on B. H of x equals the negative of x minus 2 to the 4th plus 5.
No, I'm kidding. Hear me out. I got a. Oh, hold on.
Let's talk transformations here. Hopefully that's where Logan is starting us. Go ahead.
I have a. It moves vertically up 5 because that plus 5 outside.
Okay.
You want another one? I'll give you another one. Logan, oh, thank you. And I got it moving right too because mine is 2 on the inside.
Okay.
I think P Money's got this next one. Hit us up, P Money.
I ain't got it. It's all you.
Hit us up, P Money.
It's all you.
All right.
We got the right 2.
Go for 2.
The up 5.
I mean,
Go for it, Logan.
that negative out front, it's going to reflect it across an axis.
Which axis?
Or
I think this is why he's trying to get this one off.
X-axis.
It is the x-axis.
Yeah, because
Okay.
the y-axis is out front of the h of x, right?
The
No,
y-axis
it's inside. It's inside.
is on the x. So when you're reflecting across, listen, when you reflect across the y-axis, the negative is directly on the x. If your negative is out front, it reflects across the x-axis. And what graph is this all being done to?
The fourth.
Y equals x.
Y equals x to the 4th, yes? So we're going to reflect the graph of y equals x to the 4th across the x-axis and translate right 2 and 5 unit and 5 up. So I'm going to start with,
Does the order matter?
it does in terms of whether you reflect first or go up or down 5.
So yes,
The-
it does matter.
Reflect and left right, it doesn't matter which of those comes first, but that up 5, it needs to be the last thing done. So that's why I'm putting my reflect here first. We're going to reflect the graph of y equals x to the 4th across the x-axis and translate right 2 and up 5 units. Okay. As I put some tick marks, I go up and down 5 and left and right 4. Let's start with, what does the basic graph of y equal x to the 4th look like? Have we talked about that one?
We haven't, but I computered it. And I know what it looks like somewhat, I think.
You computed it on the calculator?
Yeah.
No, I don't think I did.
These calculators are essentially
Right,
computers.
just take the x value and you just.
Yeah, I was going to say it's
Okay. So if we put in 0, what's 0 to the 4th? 0. When you put in 1, what's 1 to the 4th?
1.
1 to any power is 1. While we're here, when you put in -1, what's -1 to the 4th?
1.
It's also a positive 1. When you put in 2, what's 2 to the 4th?
16.
And a boy.
2, it's way up there, yes?
Year.
And what do you think -2 to the 4th is?
I will think it's gonna be like 16.
It's going to be 16. So realize, and I don't know if that's exactly where 16 is, but here's what I need you to realize. This kind of at first looks like what?
A parabola.
It looks like a parabola, but here's the deal. It
Straight.
kind of has, the bottom is a little bit fatter, okay, wider, but then other than that, it goes up steeper. And so when you look at, it's going to do something more like that, okay? Now,
Like that ballard.
what do we have to do with this graph?
Just basically reflected across the x-axis. So like 0, 0 stays the same. And then you just take positive ones and make them negative ones.
Okay, reflecting across the x-axis is going to make it's a U shape, okay? It's just slightly different than a parabola U shape. We're going to take it, flip it upside down, and then take that vertex and move it
Left, right, up, down. Well, okay.
right 2 and up 5. So I'm going to go right 2, up 5. There's my new vertex. Instead of going over 1, up 1 both directions, because it's reflected upside down, I'm going to go over 1,
Down 1.
down 1 both directions. Technically, the other part would be going over 2, down 16.
Somewhere in
My graph is going to be something like that.
Alright, let's computer this.
Now, I don't really have a y-intercept at this point, do I? We can figure one out, because what is it? It's at 5 up. Where would you expect it to cross? If you go over 2, down 16,
At negative 16.
from 5 up, going 16 down, negative 11.
Yeah,
So you just plug in.
Now, let's see, does it compute? If you plug in 0, the negative of 0 minus 2 to the 4th plus 5. 0 minus 2 is negative 2. Negative 2 to the 4th, 16. But it's the negative of 16 plus 5, which is going to be
11.
negative 11. Is that what you would expect?
That's what I was expecting personally.
Yeah. It's not on my graph, but it makes sense. Okay. Now, one thing that I want to kind of show you so you guys are aware, or if you have your calculator there by you, take on your calculator and graph y equals x squared versus y equals x to the 4th. Because I want you to be able to see what is the true difference between y equals x squared and y equals x to the 4th.
That boy big. We hit it with the zoom in. It could have been a snicker.
Validating.
Okay, there we go. Sorry. Okay, guys. I had went ahead and graphed mine.
Validity.
My blue is y equals x squared. My red is y equals x to the 4th. Do you see how the red goes up steeper? As it should. 216 versus 24. That was on a standard screen. If I zoom in, you can see the difference in the bases. Okay, how the x to the 4th has a wider base X squared is a more rounded base. Okay? That's your basic x sub fourth. And we're going to talk more about x sub fourth graphs. But I want you to kind of see, it's not exactly a parabola, is it? It's similar, but not exactly. Okay? Okay, questions before I continue on? Okay. In our next example, we are asked to graph the polynomial function and locate its extrema and zeros and explain how it's related to the monomials from which it is built. Okay, so we've got several pieces happening here. Now, okay, I don't have any information on mine that indicates that I graphed that by hand. So, what am I going to tell you to do?
Computer it.
We're going to put this on the calculator.
Computer. Have some computer in this? Get that boy. Get that computer.
So x to the third plus x. I'd go for your standard Zoom screen.
Oops.
Okay. What's that graph look like to you?
Kind of like a x cube with a little skinny end of it.
Okay. Kind of looks like an x cubed graph, doesn't it?
Not as curved. Yeah.
Okay. And we're going to talk about that because it looks like an x cubed. But is it exactly x cubed?
No.
It has the general shape. Now, so here's what I want you to do. Type in an x cubed graph and compare them. It's very similar, isn't it? Blue is the problem we're working on. Red is just your basic y equals x cubed on my screen.
That's what we
It's very similar, yes?
I feel like the same with mine.
What is the other portion of this graph? So part of this graph is x cubed. What's the other portion? The other portion is just an x, yes?
here.
Okay, well, let's investigate. I'm going to do a third graph here.
Ice cream.
Y equals x, because that's the other piece that it's made up of. Now, I'm going to graph it. It doesn't really look anything like it, does it?
Not per
But-
se.
I'm going to zoom in because I want us to focus on the origin. If I zoom in, remember when you zoom in,
That's out.
at first it's asking you where to zoom in. Well, my cursor is on 0, 0, that's where I want to zoom in. I'm going to hit enter again. And when I zoom in, okay, there's my blue graph we're talking about. Red. What do you notice about my line and my original blue graph?
It follows that X
Okay.
on that line.
So in other words, if I take out just the plain x cubed, so there's x cubed plus x,
It follows that.
what does y equal x do right there at the origin?
They cross.
And they do even more than cross, it looks like. It looks like they follow each other
Yes,
some,
I'm saying.
doesn't it?
That's what I'm saying.
So the idea of this graph is that y equals x cubed plus x. In general, it's the shape of
The X cube.
x cubed. But near the origin,
It follows that X.
it follows y equals x. It has more of the shape. In other words, it has that straight line of y equals x. Okay? So that kind of talks about the section of explain how it's related to monomials from which it's built. Now, let's back up a moment. Let's talk about extrema. Do you remember the vocab word extrema?
New.
Extrema is a fancy word.
We should just make it not a fancy word.
It's a fancy general word for mins
Local thing.
and maxes.
Access on that.
When you are asked, and folks, this is important, you've got to, extrema is one of those words you've got to stick in your head as, okay, that's pre-calc vocabulary we've got to know. Okay? Are there any, or it said to locate its extrema? What do you see in the way of mins and maxes here?
I got none.
Okay. My graph is going to go infinitely low. It's going to go infinitely up. Do we have any local mins or maxes in the middle?
Not really.
No. So on this particular graph, I'm going to say no extrema. And what I'm saying there is that there are no specific mins and maxes. Okay, no extrema. The next part we're asked to identify are zeros. Another good vocabulary word. I think you might have a better idea of this one. What are zeros? What is a zero on a graph? No?
Somewhere where the graph touches an axis.
Which axis?
X.
Okay. Your zeros are your x-intercepts. Okay, and again, and that's a vocab word you saw in algebra, definitely. But that's a vocab word we've got to know going forward. Zeros are places the graph, that's your x-intercepts. Okay, what do we have in the way of x-intercepts here?
Zero, zero.
We have a zero at, and I have it in my notes as just at x equals 0. So there's an x-intercept at x equals 0. Agreed?
Second.
Okay. And then the third part we've already talked about, and that was to explain how it's related to the monomials from which it's built. Okay? And so here we're going to talk about overall, the shape is like x to the third. Near the origin, the shape or the slope, you could say, is like y equals x. Okay? So I'm going to say shape is much like y equals x cubed near the origin. The shape, or I'm going to say slash slope, is like y equals x. Okay. So it's that exploration of the fact that y equals x cubed plus x. It relates to x cubed because it looks like an x cubed graph, but it also looks like x because that affects the specific origin. Okay. Are we ready for B?
Born and raised,
B, all we have is one little sign change.
but it does a lot.
Okay.
Never just flip.
Does the graph change?
It's gonna flip.
What's that graph do?
Well,
Something
it's,
on the graph.
I mean, calculator wise, I mean, she kind of has a little more extrema.
I'm going to do a zoom 6 so I can take us back out to that graph.
So it's gonna follow y equals negative x.
Yeah, fact.
It still looks like x cubed in general, doesn't it?
Yeah.
Like if you look at the overall shape, it's an increasing graph overall. It starts low, ends high. It looks like x cubed, except at that origin. So if I go back and zoom in, notice we have a little bit more going on here, don't we?
Oh, we so do.
So now,
Look. Hit him with a maximum.
we've got the difference there in the origin. Okay? So, let's talk, first of all, extrema. Do we have extrema?
Yes, we so do.
What do you see in the way of extrema?
I mean, you got a minute max.
There's a max. There's a min. Well, let's find them. Because it said to locate its extrema. The calculator can do this for us, yes?
I don't know, kinda, yeah. Probably. It does. It did. Your maximum is at negative 0.577. I mean, there's more decimals.
Do we remember how to do max real quick?
Yeah.
Second, and then the trace menu, or it's the calc menu. You go down to max. It asks you for a left bound, so you gotta go left of the highest point. It asks you for a right bound, so you gotta go right of the highest point. I guess you really don't even have to do anything, but officially it's go back to that area. Notice, I know it says max. I know it's my maximum when it tells me down there. It says max, yes?
Max.
So I just have mine at 2 decimal places. So and there's a maximum at negative 0.58, comma, 0.38. Now, keep in mind, if you're asked where the max is at the x value of negative 58 hundredths. What is the max? The max is that height of 38 hundredths. Okay? And then can you also find a min?
Yeah, negative, or not negative, sorry, 0.858, geez, 0.58, and then negative 0.38.
Yeah. This graph is very symmetric, isn't it? If you go in and find your min, it is the same values, just opposite signs. So second calc, now I pick minimum. My left bound, I need to be left of that lowest point. Right bound, I'm right of that lowest point. And I guess I just go back to my lowest point. Notice I know it's my minimum, so it says minimum, yes? Sorry, I don't know how much we've forgotten already about the calculators, so.
That was him. Paxton forgets nothing.
Okay, those are my extrema, mins and maxes. What about zeros? Do I have any zeros?
Yeah, the origin. 0.
There's a 0 at 0.
And then there's a 0 at.
Hold up.
Are there other zeros this time?
I got negative. Are they the ones?
We're crossing the x-axis 3 different spots, right?
-1.
So you should have 3 zeros.
Yeah.
You can eyeball it and say, okay, it kind of looks like that. Now remember, if you use trace, if I hit trace and then I type in, say, 1, it takes me to 1, 0, so I can see that it does cross. But also remember, you can just do second calc, and number 2 is 0, yes? Now left bound is left. Right bound of right of where it crosses the x-axis, and then there's your guess. So if you do some checking, we do have zeros at -1, 0, and 1. Okay, and I'm going to say overall shape is much like y equals x cubed but near the origin the shape resembles y equals -x. And I forgot to show that on the calculator because it is kind of interesting to look at.
I'll do the W. That's a W. Get that with the insert.
Okay, so there's my original graph. There's the red graph, which is just y equals x cubed. They still look a lot alike, don't they? Until you zoom in at that center. Now, when I zoom in at the center, I'm going to take x cubed off now. I'm going to put y equals -x on. We're going to zoom in. Oh, darn it, what did I do?
Enter.
Yeah, I tried to zoom in, it didn't let me zoom in at the same point. But, notice, they're right around the origin, they follow exactly, don't they? Okay, so, I think it's kind of one of those neat things to see how they connect there. Okay, real quick. At the bottom of this page, typical shapes of cubic and quartic functions. Okay? What's a cubic look like? What is a cubic, first of all? When we talk cubic, we're talking y equals x cubed, yes? What's the basic shape? That thing there? Excuse me. What also did we just see it could do instead of just going straight up at that origin? Can it do something like that?
Can also do.
Okay, those are variations of your x cubed. That has just a little, I mean, you could even have things where, you know, bigger pieces, you could have, you know, there's lots of different, I don't know, variations you can see there, okay? Now, y equals x to the fourth. What did we learn y equals x to the fourth looks like?
Got that thicker base.
Y equals X squared.
Kind of looks like y equals x squared, but it has a broader base, yes?
Thick.
Now, some other pieces. Excuse me, you throw in some other terms, and your U shape can become a W shape. It can become
W.
a lopsided W in either way. Okay? It could become something where, I can never draw this one, where it's kind of a W, but you're kind of missing one of the humps. Excuse me. Okay? These are all different variations of x to the fourths. It all depends on what terms are included. And we will tomorrow, remind me that we need to talk about these two statements here tomorrow to get us started.
We need to talk about the new statements tomorrow.
Hey, yeah, we can talk about it.
Yeah, we need to talk